So when I first talked to Michael, I observed that I didn't think I had much of interest to say because Python has an old-fashioned implementation. It's a sort of a classic byte-coded interpreter without by default any sort of JIT or dynamic optimization or compilation. That is a very close match to the language. And he said it would be interesting to talk about what a relatively popular non-Java language actually does. And so I'll talk primarily about the standard C implementation, a little bit about some Python implementations that run on JVMs and on .NET. My background is that I worked for many years on the core Python development team. My current job, I use Python for some things, but I'm not as active in development. So that's kind of where I'm coming from. So if you're not familiar with Python, it is it's a very high-level language, sort of an object-oriented language, but inheriting a lot of ideas from Lisp. So it's untyped, but strongly checked. Most everything in the language is first class, so functions, classes, objects, stack frames.
Can I ask a stupid question?
Sure.
Is there a way to make abstract data types in Python, so like a private field of some object that some client can't access no matter what?
Not in the language particularly easily, so there's no encapsulation in the object system. Closures by choice are encapsulated, so there's no actual way to introspect on the variables referenced through a closure.
So you could maybe cobble together?
You could cobble together something. People that have wanted to do it implement a proxy in C, which acts on behalf of. Sure. So it's a garbage collected language. It has a simple, fairly easy to use module system. It's lexically scoped with the perhaps unusual property that you can only rebind global variables and variables in the immediate environment. So by high level, it has a lot of standard built-in types that are relatively powerful and easy to use. So dictionaries, hash table implementation, it has a variety of numbers, sort of standard integers, arbitrary big numbers, floating point, complex numbers, decimal arithmetic. It has lists, which are variable-sized arrays, and it has tuples, which are more like unnamed structs. The object orientation, relatively unlike Java, uses multiple inheritance. It has single dispatch and late binding, I would say, which is when I claim the language is strongly checked, I mean sort of more for the primitive types, so that if you want to invoke a method on an object, that lookup is going to happen by name at runtime, and as long as there's a method with the matching name, it's going to be invoked. The object-oriented model supports a relatively rich meta-object protocol, so you can write a meta class in Python or in C that can customize just about every behavior of the class system, from all attribute lookup, for instance, variables and methods, to a variety of operator overloading. So, sort of getting to Andy's question, nearly everything in the VM supports a lot of introspection. So by default, classes and instances are represented internally as hash tables to support these named lookups, which is a sort of a trivial implementation technique, but originally to support debugging, all those dictionaries are exposed to user code, so if you want to directly manipulate them, you can. You can, although it's somewhat expensive, access all your local variables through a sort of a runtime created dictionary. You can modify top-level names in other modules.
So does that mean I can actually remove a local variable from an object?
Yes. Yeah, on a per instance basis, you can add instance variables.
Is this done often?
Well, that's what I say. So this was originally envisioned primarily for debugging. The environment is available for you to inspect when something goes wrong. But it's more prone to abuse than I would like.
So this significantly limits your ability to do any kind of static analysis, I assume.
That's right. Right, and coming from a peculiar background, the original language implementation and the design is biased towards the notion that users are confused by compilation, and thus you should try to do as little at compile time as possible. So yeah, as I say, as you can observe, it makes optimization more challenging. It does. It has its benefits. So I worked for several years on an object database that works with the standard Python interpreter provide object persistence all through a custom meta class that provides all the loading and unloading and memory management for that. It was quite nice that we didn't have to make any modifications to the virtual machine proper to do that, and could do it all in Python. I guess I imagine that as the language evolves, an important challenge for the language design is to try to provide a way to turn those things off most of the time, to say, I don't want to use those features, and please, run my code as if they weren't available, because on the one hand, hopefully that gives you a greater opportunity for optimization, but also, it gives you much more opportunity to actually understand what large programs do, which can be surprisingly difficult. So the actual implementation is a classic byte-coded interpreter. Probably came out of a textbook written in the 70s or something. It's a very small and straightforward implementation. So the entire C Python system is about 320,000 lines of code, of which the core VM is 20,000 lines, and in fact most of it is in external modules, so the POSIX interface, the threads interface, etc. And it only has a dozen active developers, none of whom are full-time. So it's sort of a system that is maintainable by a small group where we care more about correctness of the implementation than when we do about performance in general. It's just not tractable for a small group of people to maintain a larger system.
Do you have any idea how big your user community is?
No, I don't know how to speculate, but people toss around millions. I mean, there are lots of users for a surprising variety of applications. It's sort of originally developed as a scripting language and used, for example, a lot in high-performance computing as sort of the scripting and steering language component. But I worked on an object database that supported an application server used for web development and content management, and there are a variety of end-user applications that are developed from IDEs for Python to information management, mail sort of applications.
So, I mean, the shocking fact is that the user communities for Perl and Python may be bigger than for Java.
That's kind of what I was getting at.
Yeah, yeah. But given that it's sort of a small-scale open source project, but I wouldn't know how to guess at how many users there are. Sort of the annual, the only proxy I know of is that the annual sort of user conference draws, 400 or 500 people.
So you score high on the user to developer ratio.
That's right. So that's sort of the standard Python interpreter. There's also Jython, which was implemented on top of the JVM, and IronPython, which is a new sort of experimental implementation on top of the common language runtime. Interestingly, those were both done primarily by one person, Jim Huguenin, who's now working at Microsoft on .NET. All three of them share the property that they're really easy to extend and embed in their host environments. So in Jython, you can create a Python class that inherits from a Java class, or you can create a Java class that inherits from a Python class. And the same is generally true in IronPython. So the translation there is very natural, and the CPython implementation is straightforward to embed in an Apache web server or extend to call on your scientific code. So memory management in this implementation is also straightforward. Everything is unboxed, everything is heap allocated. The result of that is that there's a very high allocation rate. If you'd have an integer-intensive program, you'll allocate and deallocate new integers for every intermediate value computed. The implementation uses reference counting primarily, with a separate, more expensive pass to detect cycles and collect them. So one consequence of those two things is that objects consume a lot of memory. For collecting cyclic trash, there's a doubly linked list of all container objects, which is adding 16 bytes of overhead given the language constraints. plus a reference count field, a pointer to the type information. Sort of most obscenely, you might say, instance variables are stored in a dictionary, so the minimum size for a dictionary to store, up to 5 instance variables is 144 bytes. So, a Python is a very heavyweight runtime in that sense. So luckily, you can get 6 gig boxes these days. There are a number of optimizations at the low level to sort of deal with the very high allocation rate. So there's a custom small object allocator, basically segregated free lists with pool sharing for the unused space. And there are also type-specific free lists for things like integers and the heap allocated activation records, because those churn through even more quickly. And in fact, some set of integers are just allocated statically and reused. So in terms of multi-threading, Python uses whatever platform thread support there is. It has the limitation that only one thread can be actually running in the virtual machine at a time, and so